Hello everyone, my name's Connor. I'm a PhD in physics at the University of Glasgow, and tonight I want to talk to you about one of humanity's greatest inventions. Now, when I say that phrase, humanity's greatest inventions, what sort of things come to mind? Please feel free to just shout out. Dishwasher. Got any more? What? Bread, sliced bread. Any more? Fire. That's okay, right, we're going well back for that. Okay, but tonight the invention I want to talk about is the fridge. Now, before any of you start falling asleep at the idea of me talking about fridges for the next 10 minutes, I'm fairly confident that after this talk, I can convince you that the fridge is one of humanity's greatest inventions. You see, the way the fridge works is we have essentially two compartments. One part is the evaporator, and the other part is the condenser. And within our fridge, we have a gas that we call a refrigerant. And this is constantly being cycled through a refrigerator. And this is how our refrigerator operates and how we're going to cool it down. So as our refrigerant gas enters the evaporator, we cool it down and it becomes a liquid. And when it's in this cooled state, it's going to start absorbing heat out of our refrigeration compartment. And this is how we're going to cool it down. As it does so, the liquid's going to heat up and it's going to evaporate back into a gas. We're then going to compress it here, and this leads to a buildup of pressure and a buildup of heat as a consequence. And this is going to be ejected in the condenser. And as it condenses, it was going to eject the heat, and this is where, if you've ever placed your hand behind the back of your refrigerator and wondered why it's so warm, this is why. And as it cools down, it's going to eventually come back here and condense into a liquid again. And the cycle is going to continue over and over again. And your fridge is doing this millions of times just to keep your food cold. We also use it to preserve medication as well. And this is also the same principle of how air conditioners work. And if we run this process in reverse, you can actually build a heat pump for heating rather than cooling. And we use these devices every single day without even realizing what we're doing, that it's even operating. And we rely so heavily on them. And as a result, that's why I think these devices are one of humanity's greatest inventions. But, and there's always going to be a but, your fridge has a dark secret. You see, 15% of greenhouse gas emissions come from the heating and cooling sector, which your refrigerator forms a part of. So these gases that you're using to cool down your food are actually warming the planet. And not only that, but there are associated risks with flammability, and in some cases, these gases can even be toxic to us and nature, or our environment. And so if we don't dispose of our fridges properly at the end of their life, these gases can escape into the atmosphere and can have horrible consequences. But what if that didn't have to be the case? You see, all of these issues that I've just highlighted stem from the fact that we're using gases to cool a refrigerator. But what if we used a solid instead? We could get rid of all of these consequences if we just used a solid rather than a gas. What if I told you that these solids already exist, and not only do they exist, but you've all seen one of these, likely even as recent as today? If you'd all like to do me a favor and open the envelopes on your desks and tell me what you see inside. Just shout out. Elastic bands, yes. Elastic bands, or otherwise known as rubber, is something we call a caloric material. Now, if you want to pass those elastic bands out around your table, there probably isn't enough for everyone, but you can just share. And what a caloric material is it's a solid material that when you apply external pressure, it heats up, and when you release it, it cools down. And so I'd like you all to try this with me. Ooh. So if you take your elastic band, and I want you to stretch it. Just be careful, don't hurt anyone at your table. If you stretch it and you press it against your skin, you should see that it feels slightly warmer. That's what we're seeing here. And this is the heating aspect of the caloric effect. And when you release that strain, so if you stretch it, it feels warm, and when you release it, it should cool down. Obviously, this is only happening at a few degrees, so it's not that extreme. But this just shows you the caloric effect in action. And in fact, people have gone as far as to design refrigerators using elastic bands. So here we have a motor with elastic bands attached to it, and as the motor spins, it's continuously stretching and de-stretching the elastic bands, heating them up and cooling them down. And as a result, you can see here that this model refrigerator is slightly cooler than its surroundings. Now, obviously, this is very warm for a refrigerator, but this just gives you an idea that if we have other caloric materials, like rubber, but more efficient, we could, in theory, build a solid-state refrigerator. Now, like my gran, you probably have similar questions, which are, Connor, this is all fantastic, but what do you actually do? Well, I study a kind of caloric material called a frustrated magnet. Now, before I go into explaining what that is, I think it's best for me to discuss something that you'll all be familiar with, which is a magnet. So in a magnet, you have your atoms, and all of your atoms are going to have something we call a spin. Now, you can think of a spin as basically an arrow. And wherever this arrow points is the direction that the magnetic field wants to go. And so in traditional magnets that you'll all be used to, the spins all like to line up. So in this case, they're all pointing in the same direction. And in this case, they are opposing each other, but they're all still aligned with each other. And this is very favorable. They are very comfortable in this position. So I'd like you all to help me in demonstrating what it's like to be a magnet. So I'd like you all to imagine that your table is a magnet. And all of you represent atoms in this magnet. And your arm is going to represent your spin. So what I want you to do is you can just point your arm out. Don't hurt anyone, please. You can point your arm out, and you're in a non-magnetic state right now. So what that means is that your spin can point anywhere you want. Yeah, on you go. Yeah, so you can point anywhere you want right now. But in the next 3 seconds, I'm going to put some pressure on you. You're going to become magnetized. And what I want you to do is try and help me form a structure like this. So to do that, I want you to point at the person sitting next to you, but only if they're pointing at you. Can you all do that for me? So I'll give you 3 seconds. 3, 2, 1. Okay. Okay, let's see what kind of structures we've got. I see some people not pointing. Oh, we got someone over there who doesn't seem like they know what to do. So, Fred, can you not point at anyone? No, so here's an example. So some of you seem to have very nice aligned magnets, but in a case where we don't have all of our atoms properly aligned, say like this, what are our spins supposed to do? Because now they can't line up with each other, as my friend Fred was just demonstrating. Well, they don't line up. They form these sort of weird, interesting magnetic structures, which this is where the frustrated magnet is born, like what I just mentioned previously. And so the spins don't like to be in this sort of structure because it's unfavorable, and this leads to a buildup of frustration and consequently heat. So in this case, we have our non-magnetic structure like you guys just demonstrated for me. But when we apply pressure, it's going to form its frustrated magnetic structure instead, and it's going to start generating heat as a consequence. And when we release the pressure, it becomes non-magnetic, and it cools down and is going to absorb heat from its surroundings. This sounds incredibly familiar to the gas refrigerator that I just discussed at the beginning of this talk. And so just on that principle, we can change our refrigerator system from something like this to something that looks like this. So it looks incredibly similar, but instead now we have our frustrated magnet caloric material here inside a pressure cell. And rather than having a gas flowing through, we now have a liquid like water, something that is non-toxic and is abundant. And so what we do is we pressurize our caloric material. It's going to heat up, and it's going to eject the heat out the back of our refrigerator, just like our gas. And when we release the pressure, it's going to cool down, and we're going to absorb heat out of our refrigerator system. And so just like that, we've gone from our gas refrigerator and changed it to something with a solid, which is both safer and environmentally friendly. And so what I'd like you all to take away from tonight is that fridges are a fantastic piece of technology. When you go home and you open your fridge, I just want you to take a moment just to think about how much we rely on these devices and how important they are to everyday life. Sadly, there are some associated problems like flammability and toxicity, but it doesn't have to be that way anymore. You see, now we can design refrigerators using solids instead of gases and build greener, more environmentally friendly devices. And so like our caloric material, we might get frustrated under pressure sometimes, but as long as we keep cool, just maybe, we can change the world. Thank you very much.